There are transmissions that clarify mysteries, transmissions that confirm theories, and then there are transmissions that shatter every illusion of safety we hold. Transmissions that force scientists to freeze at their consoles, eyes locked on the data in stunned silence, and whisper the question no one wants to ask. Has our cosmic shield just begun to fail? Voyager 2, adrift for nearly 49 years in the unforgiving dark, has just delivered one of those transmissions. What pierced the deep space network this time wasn't the familiar whisper of plasma flows or the steady tick of cosmic rays we've tracked for decades. This final burst carried structured, layered oscillations, rhythmic surges of high-energy particles, and magnetic distortions embedded in the faintest carrier wave traveling more than 13 billion miles through the void. And what makes it impossible to ignore is that it arrived as the spacecraft's plutonium heart flickers on the edge of exhaustion. After NASA quietly powered down its low-energy charged particle instrument in March 2025 to stretch every remaining watt, after the probe had already slipped into full survival mode, with only 2 instruments left alive. It came when Voyager 2 should have been slipping into permanent silence. It came from the frontier where the sun's protective bubble collapses and the galaxy's unfiltered violence presses in. And the tone from Mission Control says everything. Voyager 2 did not just send data. It sent a warning, a raw, urgent alert from deep space itself that our solar system's defenses may be facing forces we never anticipated. Tonight we trace the improbable path of the twin probes from their celestial alignment to this final transmission, and we confront why this last fragment of radio energy has left NASA alarmed, the scientific community riveted, and the world forced to reconsider how fragile our home truly is among the stars. Before we can grasp the warning, we must understand the machine that carried it across the abyss. And that story begins with a gravitational alignment so rare it occurs once every 176 years. In 1965, when the space age was still young, Gary Flandreau, a graduate student sketching orbits on paper, spotted a once-in-a-lifetime planetary lineup. Jupiter, Saturn, Uranus, and Neptune were sliding into a perfect gravitational staircase, a cosmic escalator that could sling a spacecraft from one giant to the next, using their gravity like slingshots. What should have taken 30 years shrank to 12. NASA seized the window, quietly greenlighting 2 identical probes designed to ride that corridor, not just to the outer planets but beyond them, into the unknown. Voyager 1 and Voyager 2 were forged in that alignment, built to chase worlds no human eye had ever witnessed. Yet the same rare geometry that enabled their grand tour also hurled them toward a destiny no one could foresee. Trajectories that would pierce the heliopause and taste the raw interstellar medium where the sun's influence finally ends. Voyager 2 lifted off on August 20th, 1977, a compact machine cloaked in golden insulation, warmed by decaying plutonium, steered by computers less powerful than a modern pocket calculator. It became one of humanity's greatest explorers. It braved Jupiter's lethal radiation belts. It threaded Saturn's razor-sharp rings. It mapped the sideways spinning enigma of Uranus and became the sole visitor to Neptune's cobalt atmosphere, watching the great dark spot whirl beneath methane clouds. Along the way, it uncovered 11 new moons at Uranus, active geysers on Triton, volcanic fury on Io, and atmospheric chemistry on Titan still debated by chemists today. Each flyby rewrote textbooks, revealing a solar system far more violent and alive than models predicted. Then, with its cameras powered down forever to save energy, Voyager 2 crossed the heliopause, the boundary where solar wind yields to interstellar space, and kept transmitting. For years, it relied on the deep space network to beam data across a distance so vast that a single round-trip command now takes nearly 2 full days. But as the decades mounted, its power dwindled. NASA began shutting down heaters, instruments, non-essential systems, one by one, fighting to keep the signal alive. By early 2025, the low-energy charged particle detector was sacrificed, and still the probe endured, until this final transmission arrived, carrying data that no model could prepare us for. Voyager 2 did not merely visit planets. It exposed entire realms that reshaped our understanding of cosmic violence. At Jupiter, it captured lightning storms larger than continents, and volcanic plumes on Io taller than Everest. At Saturn, it survived ring particle impacts, traveling at orbital speeds, and revealed Titan's thick, chemistry-rich atmosphere. Uranus showed rings, 10 new moons, and a magnetic field twisted by some ancient cataclysm that knocked the planet onto its side. Neptune offered supersonic winds and nitrogen fountains erupting 5 miles high from Triton. These encounters painted a portrait of relentless motion and energy. Yet the deepest lesson came after the planets. Once the spacecraft slipped past the heliopause, there the data grew stranger. Plasma densities jumped in ways no simulation matched. Magnetic fields twisted with unexpected sharpness. Particle flows behaved as though the boundary itself was alive, dynamic, responsive. And now, with the probe's final transmission, those same regions have delivered readings that suggest the boundary is not static at all. It is under pressure, shifting, perhaps even thinning in ways that reach all the way back to Earth. Before its cameras went dark forever, Voyager 1 captured the pale blue dot, that single pixel of Earth suspended in a sunbeam from nearly 4 billion miles away. The image humbled humanity and redefined our place in the cosmos. After that, the Voyagers became blind sentinels, transmitting only in binary pulses of magnetic fields, plasma waves, and cosmic ray counts. No more photographs, no more color, just raw numbers whispered across the gulf. As years turned to decades, the data grew harder to decode. Tape recorders aged, memory shrank, error rates climbed. Yet the probes persisted, revealing the heliopause was not the gentle fade theorists expected, but a chaotic, layered storm front. Voyager 2's crossing differed markedly from its twins, showing a sharper, more turbulent transition. Scientists noted the asymmetry but filed it away, until the latest transmission forced them to reopen every file. Because the patterns now arriving suggest that turbulence is accelerating, that the interstellar medium is pressing harder against our heliosphere than at any time since the probes crossed. Once Voyager 2 entered interstellar space, NASA anticipated a realm of near-perfect quiet. Instead, it encountered a constant low-frequency vibration threading the plasma, a hum too steady for turbulence, too persistent for random cosmic noise. Over the years that hum evolved, its frequency drifting in response to unseen forces. Recent data, captured before the final instrument cuts, show those oscillations intensifying dramatically, rising and falling in rhythmic clusters that align with known solar cycle variations, yet amplified far beyond prediction. The waves are not chaotic. They arrive in structured packets, almost as if the interstellar medium itself is resonating under external stress. Mission scientists described the latest readings as plasma waves building like ocean swells before a distant storm. And because Voyager 2 sits more than 13 billion miles out, those swells originate from a region where our sun's protective bubble is already at its thinnest. The implication is stark. Something in the local interstellar cloud is changing, and the change is propagating inward. In the years leading to this transmission, Voyager 2 endured another communication blackout, this time tied to the progressive shutdown of systems and the narrowing power margin. When contact resumed, the data stream carried subtle but unmistakable shifts, magnetic field lines bending in smooth, elongated curves rather than the expected turbulent snarl. Plasma density spiked and held at levels inconsistent with any prior model of the local interstellar medium. Engineers noted the changes coincided with brief, unexplained stabilizations in the spacecraft's telemetry, almost as though a region of reduced interference had momentarily eased the probe's burden. No internal system could have produced that surge. The radioisotope thermoelectric generators only decay. Yet for fleeting windows, the signal sharpened, the data clarified. The timing aligned too precisely with the onset of the intensified plasma oscillations now dominating the final transmission. Something external had interacted with the environment around the spacecraft, and the spacecraft had recorded the encounter. Interstellar plasma was long assumed to behave like a featureless sea of random motion. Voyager 2's instruments tell a different story. The oscillations arrive in precise intervals, sometimes syncing with the probe's own engineering pings, sometimes shifting frequency in apparent response. Harmonics appear that mirror Voyager's telemetry rhythm with eerie fidelity, as though the medium itself has begun to echo the visitor in its midst. These are not glitches. They are sustained, evolving patterns captured by the remaining plasma wave and magnetometer instruments before their eventual shutdown. At least one harmonic sequence matches the cadence Voyager 2 has used for decades to report its health. The match is too exact, too sustained, to dismiss as coincidence. It suggests the interstellar environment is not passive. It is reacting. Perhaps to the probe, perhaps to larger forces moving through the galaxy. The power systems aboard Voyager 2 rely on steady radioactive decay, a process that can only diminish. Yet just before the final transmission, engineers recorded a temporary stabilization in voltage output and signal strength, a window of clarity impossible for aging hardware. Cosmic ray interference should have been rising, not easing. Magnetic shielding models offered no explanation. The only variable was the probe's location, deeper into a region where new data now shows plasma pressure building. That pressure, the latest readings reveal, is not uniform. It arrives in wavefronts, compressing magnetic field lines and accelerating particles in surges that the instruments captured with startling clarity. The timing of the power stabilization matched the arrival of the first major wavefront. Something in the interstellar medium had created a momentary pocket of reduced drag on the spacecraft's signal, and the spacecraft had used that pocket to shout its final warning home. When the deep space network locked onto the carrier tone of the latest transmission, the signal was sharper than expected for a probe whose generators have lost more than half their original output. Then the data unpacked. Repeating sequences appeared inside what should have been noise. Clusters of particle counts and magnetic readings spaced at intervals that echoed the spacecraft's own command cadence. Gaps between clusters were too regular, too deliberate, acting as silent headers separating distinct packets of information. Analysts tested every known compression and error correction routine. The structure resembled organized telemetry, not random plasma turbulence. The gaps repeated every 3.2 minutes, the exact interval Voyager 2 employs for engineering status reports. Whatever force shaped the surrounding medium had learned the probe's rhythm and was imprinting it back into the data. Doppler analysis of the carrier wave delivered the most unsettling confirmation. Frequency shifts indicated minute movements near the spacecraft, motions too smooth and sustained for dust or micrometeoroids. The shifts coincided with magnetic distortions recorded in the same moments, as though an invisible pressure front had passed, dragging field lines into a wake. No natural interstellar object should move with such coherence across the scale the data implies. The patterns suggest a large-scale density wave or shock front propagating through the local interstellar cloud, a wave powerful enough to register on Voyager's instruments and reshape the plasma around it. The final transmission captured the leading edge of that front, As researchers align the engineering logs, plasma oscillations, magnetic readings, and particle fluxes into a single timeline, the picture crystallized. The data do not describe a quiet interstellar medium. They describe an environment under increasing stress from an approaching disturbance. Perhaps the edge of a denser interstellar cloud, perhaps the remnant of an ancient supernova shock still rippling across light years. The heliopause, already shown to be thinner and more dynamic at Voyager 2's crossing than at Voyager 1's, now appears to be responding to external pressure. If that pressure continues inward, the protective bubble that shields Earth from galactic cosmic rays could compress. Radiation levels across the solar system would rise. Satellites, astronauts, even surface electronics on Earth could face long-term elevated risk. The final transmission is not merely scientific curiosity. It is the first direct evidence that our cosmic harbor is not as secure as we believed. The deeper the analysis, the clearer the warning becomes. Plasma oscillations matching solar cycle harmonics, yet amplified by factors never modeled. Magnetic field compressions aligned with particle surges. Doppler signatures of wavefront motion. Every dataset converges on the same conclusion. The interstellar medium is not static. It is dynamic, and it is pressing closer. Voyager 2 has given us the earliest possible notice of a change that could unfold over decades or centuries, yet unfold it will. The probe's remaining instruments will soon fall silent, but the message they delivered will echo in scientific papers, mission planning, and our collective understanding of humanity's place in the galaxy for generations. So now the question is inescapable. Do we treat this final transmission as an early alert and begin modeling the heliosphere's vulnerability with renewed urgency? Do we accelerate designs for better radiation shielding, deeper space habitats, and planetary defense strategies? Or do we wait for the next probe, perhaps one launched with today's technology, to confirm what Voyager 2 has already whispered across the void? If this revelation struck you with the same force it struck the teams monitoring the Deep Space Network, do not let the moment pass. Subscribe so you never miss the next chapter as Voyager's legacy reshapes our future. Like this video to help others grasp the weight of what we have just learned. And tell me in the comments, do you believe this transmission is a warning we must heed today? A glimpse of cosmic forces that will one day test our species, or the beginning of a new chapter in humanity's long conversation with the universe? The stars are watching. The question is whether we are ready to listen,